Good morning, everybody. My name is Carlos Angarita, and we're group number 2, formed by Grandel Vasselais, Hamish Newton, and myself. We're going to expose about our concrete design project titled Proposal of Concrete Warehouse for Heavy Storage in Vineland, New Jersey. The picture on the left is our final design modeled in visual analysis, and our right one is our final design modeled in Revit architecture. This is our table of contents. Each of these titles represents a chapter in our final design report, addressing each of the tasks presented in the guidelines, in addition to one last slide presented here with a video of the structure modeled in Revit. Here, we will be covering the concrete mix design, the preliminary sizing of the elements, the structural modeling itself, and the design of several structural elements, such as slabs, beams, and columns. So first of all, any project has to specify the location where the structure will be built. In our case, it takes place in a flat lot in Vineland, New Jersey, at the northeast quadrant of the country. The building layout was provided by the owner of the lot with the preliminary locations of the columns, according to the architect desire. For group number 2, the horizontal spans center to center were 35 feet long, excepting the span DE, being 34 feet long. On the other hand, the vertical spans were 14 feet center to center of columns. The concrete mix design was performed to calculate each of the components of the mix. Then, the preliminary sizing allowed us to model each of the members calculated for their respective analysis. Consequently, all the calculations were verified with a software such as S-Line, S-Concrete, among others. Finally, economical implications were analyzed in regards to the different columns designed. The picture at the bottom left is a render of the proposed structure, followed by the verification of the T-beam and by the one-way behavior of the roof slab. As engineers and designers, we proposed the materials that would create the required mix to resist the loads that will be present in the project. As a personal owner request, it was required a concrete compressive strength of 4.5 kSI. According to the first table at the top right, the required average compressive strength that the concrete must have is shown to account for the uncertainty of the conditions when the concrete is cast. Then, the table below allowed us to get the water to cementitious ratio for air-entrained concrete. Following the same procedure, the different tables and figures shown in the project report allowed us to get the air and water content for then adding all the materials to use total volume relationships and solve for the volume and mass of the fines. Here, the first table shows the results of our group, while the figure below exposes the concrete union software results. Then, Table 9 at the bottom presents a comparison of both calculations to prove that all values calculated were within the 10% of error, which makes our group calculations to be correct. The final masses by cubic yard were then 188, 628, 1763, 1254, and 3833, respectively for the water, cement, and coarse and fine aggregates.
For this task, the relevant gravity loads that were applied to the structure were found. This consisted of snow and rain loads, which were calculated using equations in ASCE 716. Also, the live loads and dead loads were found, and these were specified in the project outlines. As you can see, the table shows the exterior roof unfactored service loads. The roof dead and live loads, as well as the rain and snow, are all very similar, whereas the initial self-weight is significantly larger. The initial self-weight was calculated using preliminary sizing designs. This table then shows the interior unfactored service loads. Most of the values were specified in the project outline, however, the live load for the structure was also found in ASCE 716, considering the structure as a heavy storage warehouse.
This task was divided into 5 sections. For the slabs, we used the ACI table 7.3.1.1, from which were arrived to an 8 inches of thickness slab. For the beams, we used the deflection equalization method, since we know the maximum permissible deflection for structural members. Then, this deflection was equalized to the acting deflection of the member by the loads to solve for the inertia. And from there, by setting the base as 1 feet, we found the minimum height for the beams. For the T-beam, it was used the same method in addition to the consideration of the Steiner's theorem. This one states that the total inertia of a composite section is the sum of the separate inertias plus the factor of the respective area with the square of the distance between the centers of each object to the total center of the composite section. For the columns, we used the formula given in the textbook by James White. And finally, for the footings, as the soil bearing capacity was given, the dimension of each footing were obtained according to each different column load. In this task, the nodes were drawn first, and then the elements, such as beams and columns, according to their respective dimensions. Note that the right top picture was the initial node distribution, while the left picture shows a final node distribution more complex with all the meshing errors fixed. Note also that the beams in the horizontal direction had a greater overall height than the ones in the vertical direction, given the length of the span on each direction of analysis. After this, the plates were drawn and the loads were applied. Note the dead loads applied in the pictures and the settlement and rotation applied in the right top picture for the foundation C1. The parapet walls were modeled as a linear distributed load on the exterior girders of the structure. The picture on the bottom left showed the final arrangement of the structure modeling. Here, one can observe the one-way behavior proposed for the roof slab, given the span's dimensions and the meshing proposed. It is important to state that commonly, the success of any structural model comes from a right meshing distribution. Therefore, we modeled each of the slabs by having a 1 foot width section, by also adding a node on each of the ends of these typical slab sections, so the solicitations could be transferred accordingly.
Hi everyone, Grant here. So I'm going to briefly touch on our service dead load analysis, which was task 5. The main goal for this task was to perform an analysis on our model using only service dead loads. Now our model check information came back clear and there were thankfully no errors found in the model. However, the result check information did indicate a few design errors. Thankfully these can be neglected as we're using the educational version of visual analysis, which does not perform design checks. Now the second portion of this task was to verify the results for our model by comparing it to hand computations for column 2. First, we took a look at our results for column A7, which is the corresponding column in our model. As you can see, it is in the corner, it is an exterior column. And taking a look at our shear moment diagrams, everything appeared to be in order. Now for our hand calculations, I'm just going to go over our axial computations, just for the sake of time. To begin, we drew a free body diagram of our member A7, and from there we calculated a superimposed dead load from our slab of 115 pounds per foot squared. If you multiply that by our tributary area, it yields a load of about 14,000 pounds. The next step was to add the self-weights for our beams and our CMU, and in total this was about 8,000 pounds per foot squared. Now if you add these two things together, you have a ultimate axial load of about 22.18 kips, and this was only 0.4% off of what our model had yielded.
The factored load analysis was carried out in visual analysis. A customized building code that reflected the load combinations within ACI 31819 section 5.3 was created within our model. The deflection load combinations were added to this customized building code, and we also decided to create an extra load case including the settlement factored load to be more conservative. The model was then run, providing a short-term analysis of the structure as shown in the picture. The ultimate factored load cases were determined also from this analysis. A long-term analysis was also carried out, considering the long-term effects on the structure, which included creep and cracking. To account for this, the moments of inertia for the structural members were reduced according to ACI 31819, table 6.6.3.1.1a.
For chapter and task 7, we used the ACI shear and moments coefficient method. We proved that the T-beam was prismatic along its entire length. There were just distributed loads. The service live load showed to be less than 3 times the service dead load. The T-beam C17 had 6 spans, and the length was always 14 feet since was the vertical direction. We used the ACI interval with support case to compute the moment and shear solicitations. Then, a 3-dimensional free body diagram was drawn along with all the supports, reactions, and loads acting. From this, and with the ACI method, we obtained the shear and moment diagrams shown in the right picture. In the final design for the top of the T-beam, it was chosen 5 bars number 4 and 2 bars number 7 for the bottom. Note the first row of steel reinforcement was decalculated by requirement. The second row represents the minimum by norm, and the last one is the junction of both to account for the final steel design. The shear, flexural, and torsion requirements were met and are shown in the project report. Finally, we modeled our T-beam through the S-line software, giving an acceptable steel and concrete section distribution. Note that the top reinforcement is required at the supports, while the bottom reinforcement is required through the entire length of the beam.
For this task, a slab design for panel BC34 was carried out. A spreadsheet was used for calculations while considering ACI requirements for flexure and shear. From the bending moment diagram of the slab panel, the maximum values were used in the design of the reinforcement. Due to the midspan having a positive moment, the steel reinforcement was placed in the lower half of the slab, while at the face of the column, the reinforcement was placed in the upper half of the slab. For the spreadsheet computations, two number 4 bars were used as flexural reinforcement in both the positive and negative bending of the slab. It was also determined that no stirrups were required in the slab design. The design of the slab was then made in S-line as shown in the figure.
Note here the difference between the supports for the slab. For these, the supports are rectangular beams, instead of the T-beam where the supports were the columns.
Firstly, a free body diagram was created for the analysis of column A7. As shown, all the unfactored loads are applied to this column, which were the dead, live, rain, and snow loads. The factored envelopes for the column A7 were created in visual analysis. To verify the values within the factored envelopes, manual calculations were carried out and a comparison of the moments and axial loads were made. As you can see from the table, the axial loads are very similar, whereas the moments differ significantly. These notable differences firstly may be due to the envelope providing a worst-case scenario for the loading of the column. Additionally, when manual computations were made, it was assumed the self-weight acted as an external load that could be transferred to adjacent beams and then the column A7. However, this is not the case, since the slab cannot be removed from the panel of analyses as an external load in visual analysis, due to all the area of the plate influencing the moments present at both the top and bottom of column A7.
Chapter 10 consisted mainly in the design of column 2A7. For this, the first calculation performed was the slenderness ratio. Even though the column was theoretically considered to be fixed at the bottom, we decided to set the structural member as stiff hinged for the bottom and top respectively, having an effective length factor equal to 0.81. Note that the more close one is to 1.0, the more conservative the design is. We obtained a short column design for a 12 by 12 inches initial column. However, later it was verified that just an H by H inch column could resist the loads acting on the structure. As noted at both of the top right pictures, the column showed to be in biaxial bending. This can also be observed in the red and yellow moment diagrams. The equivalent moment eccentricity method was implemented, resulting in an axial and moment solicitation that fell even below the steel ratio of 1%. However, we decided not to increase the size of the column due to spacing requirements and personal engineering criteria. Finally, the column design was modeled in S-concrete to verify that the steel reinforcement selected was the correct one to resist the axial and moment solicitations in both directions of analysis.
Alright, so task 11 was alternative column design. Essentially, we had to repeat the design of column 2 using a circular cross-section and spiral stirrups. So first we determined the maximum load case. Then we found the required gross area and the corresponding diameter of the circular section. Now this only considered axial load and not moments. Therefore we used a divisive factor of 0.6, which increased our required gross area to 20.52 inches squared. Now the corresponding diameter to this area is too small for constructability, so we decided to match our square columns and create a circular column of diameter 8 inches. And from there, we determined that based on the minimum 6 longitudinal bars needed, that we would use 6 number 4 bars. Now the next step in our design process was to check for slenderness, and we found that by the ACI code, one of the conditions was failed, and thus the column needed to be analyzed as slender. Next, we determined our gamma value, our eccentricities, and our eccentricity ratios. Now our next step is to look at our interaction diagram. Because our gamma value is a bit less than 0.6, we decided to use the 4 KSI diagram to compensate. From interpolation, we determined that our axial load per area was 0.725 KSI. And then plugging that in for our gross area check, we found that it passed, so our section was okay. Next, we determined our stiffness, our P sub C value, our C sub N value. And then from this, we determined that our mode magnification factor was less than 1, so we used the minimum ACI value of 1. Because our earlier gross area computation accounted for moment, we determined that because our moment magnification factor was 1, that our section was adequate for any moments. Now the last portion of the design process was to finalize our reinforcement. First, we designed our lap splices. From the interaction diagram, we concluded that we would need class B life splices, and our L sub D value was determined to be 17.89 inches. For class B, this value is multiplied by 1.3, which yields 2 feet. This is the same as in our square section. And then for our spiral reinforcement, our first step was to check for torsion. We determined that torsion could be neglected. Our next step was to check for shear. Because the concrete was able to carry twice of the nominal shear, it was determined that we can neglect shear in our spiral design. Therefore, the spacing was determined using the ACI code, and the minimum value was found to be 1 for our substrate, and then our maximum was determined to be 8 inches, so that is what we chose. And then finally, you'll see here our AutoCAD rendering of our proposed circular section. Task 12 was our economic analysis. Now, the primary purpose of this task was to compare column 2's square and circular designs for cost. Our economic analysis performed for each of the column designs considered material costs, heavy machinery, and labor costs. The primary material costs were concrete and steel. And ultimately what we found was that because our circular column had a lower volume and a lower surface area, our material costs for that design were slightly lower. However, what we'll find is that labor cost is ultimately king. Now, because columns are relatively low on actual material, a lot of the cost associated with columns is found in the labor. So what you'll notice from this map that I'm projecting here is that for the Northeast, specifically the Mid-Atlantic region, the wages of construction workers are very high. And so this means that labor is an outsized factor in our cost analysis. And you'll see here from this other map, the same is true for civil engineers. So what we did for our analysis was we looked at industry research for the man hours associated with the various construction items and engineering processes. And we multiplied those by our estimated labor costs. And ultimately, what we found was that the labor costs far outweighed that for the square column, and that actually made the circular column more expensive overall. A lot of that has to do with the fact that the circular column uses a spiral reinforcement, which is much more difficult to install than ties. Our final task was our design comparison, and unlike our economic analysis, this task was more qualitative and asked us to consider things like aesthetics, constructability, manufacturability, and our sustainability and environmental impacts. Now, we placed very heavy emphasis on our initial cost, our schedule, as well as sustainability, and ultimately what we determined was that through our cost-benefit analysis, that ultimately our square columns were still more valuable.
Finally, in the following slides, you will find renderings of the structure modeled in both Visual Analysis and Revit, along with 2 video animations of the structure. We hope you enjoy the material.